In today's lecture, we are going to discuss a very important quantum number which is called hypercharge. As you know, the electric charge is an additive quantum number. Similarly, there is another additive quantum number which is called a strangeness or a strangeness quantum number. And we have already studied the strangeness quantum number, which is defined for the strange particles. And for all non-strange particles, we have seen that strangeness number is 0. Since this strangeness is conserved in the production processes, as you have seen in the previous lectures, and you have also learnt that the strange particles are produced always in pairs, and that's why we say that that's why those particles were initially called strange particles. Although at present there is nothing strange about that particles, but when those particles were invented, then it was seen that the behavior of those particles was something different from the other particles invented already at that time. One of the important strange property was what? That was the particles were produced actually always in pairs, but they decay weakly. So due to the such type of strange properties, those particles were called strange particles. Now here instead of a strangeness quantum number, it is more convenient to introduce another quantum number which is called hypercharge. And actually this hypercharge is more convenient because you will see that in this case the baryons and mesons are treated on the same footing, and that's why this hypercharge is also a good quantum number. It remains conserved in a strong interaction and electromagnetic interaction, although this hypercharge does not remain conserved in weak interaction, but it remains conserved in the strong interaction and the electromagnetic interaction. So let us start to know all the important facts regarding this hypercharge. First of all, we will see how this hypercharge is defined. Actually, hypercharge is defined in a simple way as like this, that it is just the sum of the baryon number and the strangeness number. So if you denote this hypercharge by the symbol Y, then you can say that Y is equal to B plus S, where B, you know, this is baryon number and S is strangeness number. So you can simply say that the hypercharge is the sum of, or you can say the algebraic sum of the baryon number and the strangeness number. So if you know the baryon number and the strangeness number of any particle, then you can easily find what will be the hypercharge of that very particle. Okay. Now you know that this baryon number B and the strangeness number S, these two quantum numbers are not defined for leptons. Okay. And as B plus S is equal to Y, and since B and S are not defined for leptons, so definitely you can say that this hypercharge is also not defined for leptons. So if in any reaction there is a lepton, you cannot assign any value for this hypercharge. Okay. So never a question will be asked related to this hypercharge in such that in the reaction any lepton is involved. Okay. Now since Y is equal to B plus S, So you can easily find the value of y if you know the value of b and s. Now let us see some of the important facts. As you know, for any baryon, the baryon number b is equal to 1. You have already studied this fact. For all baryons, baryon number is 1, that is plus 1. So, if you want to define the hypercharge of a baryon, then this baryon number will be fixed, that will be 1. So, for any baryon, you can say that the hypercharge y is simply equal to 1 plus s. Hypercharge of baryon will be what? That will be 1 plus s. Why? Because for any baryon, the baryon number b is simply equal to 1. Okay. Now you know that for mesons, this baryon number is equal to 0. You have already studied this thing. So if you want to define this hypercharge for a meson, then that will be simply equal to the strangeness number. So for any meson, there is no difference between the value of the hypercharge and the strangeness number. So for a meson, hypercharge is simply equal to meson. I have shown here in a tabular form the values of the hypercharge for the different mesons. You can see here. Okay. In fact, in this first column, I have mentioned the different mesons, and I have mentioned in this table the baryon number, the strangeness number, and the hypercharge y of that particular meson. As you have seen that for any meson, baryon number is 0. So you can see that I have mentioned the value of b for any meson is equal to 0 in this column. You can see. And so in this case, you have just seen that y will be simply equal to s. So if you know the value of a strangeness number for these mesons, you can say what will be the hypercharge. That will be simply equal to s. And in the previous lecture, when we were discussing the strangeness number, you have learnt what are the values of the strangeness s for the different mesons. You know, for any pion, that is pi plus, pi 0, pi minus and pi 0, the strangeness number is 0 for any meson. And since s is 0, and in this case you know that this y will be simply equal to s because b will be definitely 0. So for all mesons, that is for pi plus, pi minus and pi 0, the hypercharge is also equal to 0. Okay. Now you know that for the meson k plus, that is k1 plus, a strangeness number is plus 1, and that's why the hypercharge will be also plus 1. For k minus, you know the strangeness number is minus 1, so y is also minus 1. For k0, you know this strangeness number is plus 1, and so for this hypercharge is also plus 1. Now for the anti k naught, which I have denoted by the symbol k naught bar, this is actually the antiparticle of k0, and for this the strangeness number is minus 1, and so hypercharge is also minus 1. And for eta 0, you know the strangeness number is 0, and that's why its hypercharge is also 0. So you should remember these values of the strangeness number and the hypercharge of different mesons. Okay. And you can see that in case of mesons, there is no difference between the values of the strangeness number and the hypercharge. And this is a very important objective question. You will be asked that the strangeness number and the hypercharge of mesons are equal, not equal. We can not say what will be the relation between them. Such type of options will be given, and you have to write that both hypercharge and strangeness number for mesons are equal, because baryon number for meson is 0. I hope you are getting the things. These are very important but very simple things. But you have to remember something. Okay. Now the other class of hadrons is baryons, and in case of baryons, you know that for any baryon the value of baryon number is 1. So here B is fixed and that is equal to 1. In case of meson, baryon number was 0, but in case of baryons, the baryon number for any baryon is equal to 1. You can see here. So I have mentioned the values of baryon number for any baryon equal to 1. Okay. So if you want to write the value of hypercharge in case of baryons, that will be simply equal to 1 plus S. So again you can see, if you know the value of a strangeness number, you can easily say what will be the value of baryon, what will be the value of hypercharge for any baryon. Okay. Now let us take the particular example. You know, for a proton, which is a nucleon, the strangeness number is 0 because nucleons are not strange particles, and so its strangeness number is 0. And if S is 0, you can see the Y will be 1 plus 0, that is 1. Okay. For the another nucleon, which is neutron, you know that strangeness number is 0. So for this, again, Y will be equal to 1. For lambda 0, you know S is equal to minus 1. You have seen this value of strangeness number in the previous lecture, so you should remember that. Okay. So for lambda 0, S is equal to minus 1. So what will be Y? That will be simply equal to 1 minus 1, that is equal to 0. Okay. And for sigma plus, see here, the strangeness number is again minus 1. So what will be the value of Y? That will be again 1 minus 1, that is 0. For sigma 0 and sigma minus, for all the sigma particles, the strangeness number you know is minus 1, and so for all the sigma particles, the hypercharge will be equal to 0. Okay. Now for the Xi 0 particle, you have seen in the earlier lecture that strangeness number is minus 1. So what will be Y? As Y is equal to 1 plus S in this case, so this will be 1 minus 2, and that will be equal to minus 1. Okay. And for Xi minus, this S is again minus 2, and so this Y will be again minus 1. 1 minus 2, that is minus 1. And for omega minus, you know that S is equal to minus 3, and so what will be Y? This will be 1 minus 3, and that is equal to minus 2. Okay. So I hope you have learned what will be the values of the hypercharge of different mesons and different baryons. Okay. Now, as I have told you just now, that this hypercharge Y is also an additive property, additive quantum number. It means if in any reaction you have to find the total value of hypercharge, what you will do? We will simply add the hypercharges of different particles involved in that reaction algebraically. We will add them algebraically with proper sign. You have to add, and then you will get the total hypercharge of the reactants and of the products. Okay. Now you have seen that Y is equal to B plus S. This is just the basic technique to find the hypercharge. Y is equal to B plus S. And you have learnt in the previous lecture that this baryon number remains conserved in all the three interactions. That is, B remains conserved in a strong interaction, in weak interaction, and also in electromagnetic interaction. But on the other hand, you have learned that this strangeness number remains conserved only in the strong interaction and in the electromagnetic interaction. It does not remain conserved in weak interaction. So what will be the conservation law for this Y? You can say that this Y will then remain conserved only in the strong interaction and the electromagnetic interaction. Okay? It means this hypercharge, like the strangeness number, does not remain conserved in weak interaction. Okay? Now, in fact, two great physicists, Gell-Mann and Nishijima, has given a particular formula to find the charge of a particle. Actually, charge of a particle is related to the hypercharge of the particle and the third component of the isospin. Okay? And what is that formula? You should remember this formula, which was given by Gell-Mann and Nishijima, that charge of a particle Q is equal to T3 plus Y over 2. You should remember it. Okay? This is a very simple formula. You can remember it. And you have just seen that Y is equal to B plus S. So you can also write that Q is equal to T by 3 plus B plus S divided by 2. Okay? And you know that Q is charge of the particle, T3 is third component of isospin, and Y is hypercharge. So from this formula, you can find the charges of different particles, or you can say the different hadrons we can actually find. Now, you know that for a strange mesons, baryon number B is equal to 0. And if B is equal to 0, what will be Q? You can see the formula here. If B is 0, you can see that this Q will be equal to simply T3 plus S by 2. So for a strange mesons, since B is equal to 0, so you can write Q is equal to T3 plus 1 by 2S. Okay? And for non-strange particles, S is equal to 0. You know it. For strange particles, S is not 0. But for all non-strange particles, a strangeness number is 0. You have learnt in the previous lecture. So if you are talking about the non-strange particles, then what will be charge of that particle? That will be equal to T3 plus 1 over 2B. Here S is actually 0. So from this simplified formula, we can actually find how many particles can be formed on the basis of charge you can see. So let us now see what kinds of particle type can be formed by the various choices of T, B and S. Okay. See the first choice. Let us see if S is equal to 0. It means you are talking about the non-strange particles. Okay. When S is 0, then there will be actually 3 possibilities. And what are those 3 possibilities? You can easily see here. In first possibility, we consider that the baryon number is 0 and the isospin quantum number T is also 0. And as you know that for a given value of T, T3 has 2T plus 1 values. You have learnt in the previous lecture. For a given value of isospin quantum number T, its third component T3 has how many values? It has 2T plus 1 values. And what will be those 2T plus 1 values? Those actually lies between T and minus T at a step of 1. It means when you will move from the value t to minus t, you have to subtract 1 successively, and then you will get the values of t3. Now here I have considered that t is 0. Since t is 0, so t3 will lie between plus 0 and minus 0. Is this statement correct? If you say that its value will lie between plus 0 and minus 0, a statement is not correct, because plus minus sign has no significance before the 0. Okay, plus 0 and minus 0 both are same, that is simply equal to 0. So if t is equal to 0, t3 will have only one value, and that will be 0. You can see 2t plus 1, t is 0. So 2 plus 0 plus 1, that will be simply 1. So t3 will have only one value, and that value is equal to 0. Now you can find the value of q from the formula which I have mentioned here. Actually b is equal to 0 and t3 is also equal to 0. And we are considering the non-strange particles because we have considered s is equal to 0. So s is 0, b is 0, and t3 is also 0. So from this formula you can see what will be the value of q. t3, it is 0, b is also 0, s is also 0. So q will be simply 0. You can see the formula. Okay. So if s is 0 and you take b equal to 0 and isospin quantum number t equal to 0, then we simply get that charge of the particle will be 0. Actually, this charge represents the neutral meson, okay, and eta 0 meson. Neutral meson, and that is eta 0 meson. Okay. Now the second choice, for s equal to 0, we take b equal to 0 and t equal to 1. Now see, as t equal to 1, what will be the value of t3? t3 lies between plus t and minus t. So first value we will take 1, the second value we will take 1 minus 1, which is actually equal to 0, and the third value will be 0 minus 1, which is minus 1. So this is plus t and this is minus t. Okay. So there will be three values of t3 for t equal to 1. And what are those three values? Those values are plus 1, 0 and minus 1. Now t3 has three values. b is 0. b is 0. So you can find the value of q from this formula, which I am just indicating here. You can see when we will take t3 equal to 1, see here, q will be what? t3 we have taken 1 and plus 1 plus s is also 0. So s is 0, so this will be simply equal to 1. It means in this case q will be simply equal to t3 because s is 0. And so the charges will be plus 1, 0 and minus 1. That will be simply equal to t3. And actually these charges represent the particles which is called pions. So the pions has three charge states, pi plus, pi 0 and pi minus. Okay. Now what will be actually the third possibility? You can see here we take b equal to 1 and t equal to 1 by 2. Sorry, the page has been turned, but this will be just okay. Don't worry. See here, it is now okay. So what we have taken? b equal to 1 and t equal to what? 1 by 2. And as t equal to 1 by 2, you can say that this t3 will have two values. First one will be 1 by 2 and another will be 1 by 2 minus 1, which will be minus 1 by 2. So this is from T to minus T, and so T3 is 1 by 2 and minus 1 by 2. Okay. Here neither B is 0 nor T3 is 0, but S is 0. So your formula for finding the Q will be what? That will be T3 plus 1 by 2 B plus S. So this will be simply B, because S is 0, you have already taken S equal to 0. And B we have taken actually 1. So you can also say that this is simply T3 plus 1 by 2. Now put this value of T3. When you will take T3 equal to 1 by 2, then what will be that? That will be 1 by 2 plus 1 by 2, and that is equal to 1. So you can see here I have already calculated here. Q will be 1 by 2 plus 1 by 2, that is equal to plus 1. And this actually represents the proton. Okay. Now when you will take T3 equal to minus half, you can see Q will be what? That will be minus half plus half, and that is 0, and that represents neutron. Okay. So when we consider the non-strange particles for which S equal to 0, then you have seen that there are 3 possibilities, and in those 3 possibilities what type of particles will be formed you have already learnt here. Okay. Now consider another case when we consider the strange particles for which the strangeness number is equal to 1. Okay. So if S is 1, then the multiple charge can be avoided only when multiple charge will be avoided, means there will be not, we will not consider the particles which will have actually the same charges. So multiple charge will be avoided only when you will take B equal to 0 and T equal to half. Again in this case actually there will be 2 possibilities. Only then the multiple charge will be avoided. In first possibility we take B equal to 0 and T equal to half. And you have just seen that if T is half, T3 will be what? That will be half and minus half. Now in this case S is 1 but B is 0, and T3 is 1 by 2 and minus 1 by 2. So you can find the value of Q by this formula. This will be T3 plus 1 by 2 B plus S, B plus, but you have taken this B equal to 0. So there will be only S. Okay. And S has been taken 1. So this will be simply T3 plus 1 by 2. T3 plus 1 by 2. Now since T3 has 2 values, first one is 1 by 2. So the first value of Q will be what? That will be 1 by 2 plus 1 by 2, and that is equal to plus 1. So you can see I have mentioned here that Q will be plus 1. In fact this represents K plus. Okay. Because for K plus you know S is equal to 1. And when you will take T3 equal to minus half, what will be this Q? You can see this will be 1 by minus 1 by 2 plus 1 by 2, and that is equal to 0. Okay. That is equal to 0. And so I have mentioned here that Q is equal to 0. And this is actually the charge of K0. Okay. Now the another possibility which we can take is B equal to 1 but T is equal to 0. B equal to 1 but T equal to 0. Since T is 0, so you know that T3 will be also 0. Okay. And therefore what will be the value of Q? In this case T3 is 0, so you can write Q will be what? T3 is 0, so this will be 0 plus 1 by 2 B plus S, and B is 1. B is 1 and S is also 1. B is 1 and S is also 1. Okay. So this will be simply equal to plus 1. 1 plus 1, that will be 2, and that 2 will cancel out. So in this case, Q will be equal to plus 1, and that represents actually simply the baryon singlet. Okay. Now we consider S equal to minus 1. That is, you are considering the strange particles for which strangeness number is minus 1. In this case, actually the multiple charge will be avoided only when we will consider that B equal to 0 and T equal to half. Since T is half, you know T3 will be equal to 1 by 2 and minus 1 by 2. And in this case, what will be Q? You know, Q will be T3 plus 1 by 2 B plus S. But since B is equal to 0, so this will be simply T3 plus 1 by 2 S. Now, since T3 has two values, so let us take first of all T3 equal to 1 by 2. So Q will be equal to 1 by 2 and minus 1 by 2. Why minus 1 by 2? Because S is equal to minus 1 in this example. So this will be equal to 0, and this represents actually the anti-particle of K0, that is K0 bar. And when you will take T3 equal to minus half, what will be Q? You can see Q will be minus half, that will be minus 1, and that actually represents K minus. Okay. Now the second possibility in this condition, for avoiding the multiple charge, you have to take B equal to 1 and T equal to 0. Since T is 0, you know T3 will be 0, and so in this case, what will be the value of Q? Q, you know, this is T3 plus 1 by 2 B plus S. Okay. And here T3 is equal to 0. Okay. And B you have taken 1, and S you have taken in fact minus 1. So that will be 1 by 2, 1 minus 1, and that is 0. So Q will be equal to 0. In fact, this represents actually the singlet baryon lambda 0. Okay. Now the third possibility, you can take B equal to 1 and T equal to 1. And you know, if T equal to 1, T3 will be what? That will be 1, 0 and minus 1, from plus T to minus T. Okay. And so in this case, what will be Q? You can use this formula. Q is equal to T3 plus 1 by 2 B plus S. And you know this will be T3, and since in this example we have taken B equal to 1, and S equal to minus 1. So this second term vanishes, that is 0. So Q will be simply equal to T3. And T3 has three values, plus 1, 0 and minus 1. So in this case, you can see Q is plus 1, 0 and minus 1. And actually these are the charges of the sigma hyperons, sigma plus, sigma 0 and sigma minus. Okay. I hope you are getting the things. This is very simple, and you can easily understand these facts. Now, in the fourth possibility, you can take S equal to minus 2. Strangeness number is minus 2. In fact, in this condition, you can neglect the multiple charge only when B is equal to 1 and T is equal to half. If T is half, you know T3 will be plus half and minus half. And so what will be the value of Q? You know Q is equal to T3 plus 1 over 2 B plus S, and here B is equal to, this is T3, and here B is equal to 1 and S you have taken minus 2. So this will be minus 1 and divided by 2, that is, this is T3 minus 1 by 2. Now substituting the value of T3, you can easily find what will be the value of Q. You can see the first value of T3 is half. So when you will take T3 equal to half, this will be half minus half, and that will be equal to 0. So you can see here I have mentioned that Q is equal to 0. And when you will take T3 equal to minus half, then that will be minus half, that will be minus 1. So Q will be equal to minus 1. And this actually represents the Xi hyperons, in fact Xi 0 and Xi minus. Okay. Now lastly we take the strangeness number S equal to minus 3. In this condition the multiple charges can be avoided when you will take B equal to 1 and T equal to 0. If T is 0, T3 is equal to 0, and so in this condition what will be the value of Q? You can see this is T3 plus 1 over 2 B plus S. Okay, but here T3 is 0, so this will be simply 1 by 2 B plus S, and here we have considered that B is equal to 1, so this will be 1 by 2 times 1, and S is minus 3. So this is in fact minus 1 by 2 into 2, that is minus 1. Okay. So you can see I have mentioned here that Q is equal to minus 1, and this actually represents the omega minus hyperon. Okay. So I hope you have learned that how the different kinds of particle can be formed by the various choices of T, B and S. Okay. Actually this scheme of finding the formation of particle is also known as Gell-Mann Nishijima scheme. Okay, because we have used the formula devised by Gell-Mann and Nishijima for finding the formation of particles. So this is actually called Gell-Mann Nishijima scheme. Okay. Now we will see some of the important examples of a strong interaction in which the hypercharge remains constant. When question is asked that check that any process that a process will be given, and you have to check that the process is possible, that process will proceed or not on the basis of hypercharge, then you can see the conservation principle of the hypercharge. And according to this conservation principle, the hypercharge of the reactant and the product will remain same if the interaction is either a strong interaction or electromagnetic interaction. But in weak interaction, remember, this hypercharge will not remain conserved. Now see this example, which is just an example of a strong interaction. Here you can see when there is an interaction between pi minus and proton P, then the result is actually lambda 0 plus K0. Now I have mentioned here the value of hypercharges of different particles involving in this reaction. For pi minus, y is equal to 0, just you have learnt this, and for proton it is 1. So the sum of the hypercharges of the reactants will be what? That will be 0 plus 1, that is 1. Okay. So this sum is equal to 1. Okay. And for the product, you know, for lambda 0, hypercharge y is 0, and for k 0, it is 1. So sum of the hypercharges of the product is also equal to 1. So you can see the sum of hypercharges of the reactant and the product are same, or in other words you can say that change in hypercharge in this process will be what? That will be 0 plus 1 minus 0 plus 1, that is 0. So you can say that this y remains conserved in this process or in this reaction. Okay. The another example we can take here, that when there is an interaction between pi minus and p and the result is pi 0 and n, then you can check that the hypercharge is again conserved. Here for pi minus y is equal to 0 and for proton it is 1. So the sum of the hypercharges of the reactant is 0 plus 1, that is 1. And for products, for pi 0 again the hypercharge is 0, and for neutron it is 1. So sum of the hypercharges of these two particles is also 1. So the hypercharge in this case, in this reaction also remains conserved. So what will be y? Y will be 0 plus 1 minus 0 plus 1, that is 0. And so you can say that this y remains conserved in this reaction too. This remains conserved. Okay. Actually this is just an example of the reactions or processes in which the hypercharge remains conserved. I hope you have understand the different aspects of this very important, a very good quantum number, hypercharge. And in the next lecture we will start to deal with the another important conservation principle, which will be actually the conservation principle of charge conjugation. Okay.